Good evening. I suppose I'll get started. I welcome the viewers to this problem solving and live interaction session for the subject experimental stress analysis offered by Professor K. Ramesh on the Swayam portal. So today we will be discussing the contents of the last week, that is week 12, which has to do with strain gauge, the topic of strain gauge, especially to do with transfer sensitivity and its appropriate corrections. So my name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics and Biomedical Engineering, working under the guidance of Professor K. Ramesh and co-guidance of Professor U. Saravanan from the Civil Engineering Department. So we'll get started. So let us look at the first question. It says the stress gauge construction is based on which of the following aspects? The Poisson's ratio of the gauge substrate should be negligible. The transfer sensitivity of gauge should be equal to two times the Poisson's ratio of the gauge substrate. The transfer sensitivity of the gauge should be negligible. The transfer sensitivity of the gauge should be equal to the Poisson's ratio of the gauge substrate. So let us try to understand how this comes about. By transfer sensitivity, we mean Kt. So we know for a strain gauge, delta R delta R by R is a function of the axial strain plus St epsilon T. Now here, if we were to take Sa epsilon A common, I get 1 plus epsilon T by epsilon A into St by Sa. Now we know that epsilon T by epsilon A is given as minus mu naught. So this implies delta R by R uses Sa epsilon A into 1 minus mu naught Kt, where we define the transfer sensitivity Kt as St by Sa. So this is the fundamental. This expression is fundamental to measuring strain using strain gauges. Now here, let us go further and analyze this. Let us say that we have a stress field such that we have the axial strain given by sigma A is axial stress, axial stress given by sigma A, and sigma T gives us the transverse stress. So therefore, from our basics of Hooke's law, we can see that the actual axial strain will be sigma A by E minus mu sigma T by E. Similarly, our transverse strain is given as sigma T by E minus mu sigma A by E. Now that we have the expressions for the axial and transverse strain, if we were to substitute this back in equation 1, call this equation 1. So substituting this back in equation 1, so we get delta R by R is given as, I'll just take SA. I have the expression as SA epsilon A. Rather, let me substitute it in this expression instead. So I have equation 1 as, F1 is given as this. So here, if I were to take out only SA, I get epsilon A minus KT into epsilon T, because that cancels out the mu naught. So let us substitute these in this expression. So what do I get? Delta R by R is equal to SA into, I'll just take this expression, minus KT into this expression. So this follows, if I were to cross multiply this out, this gives me minus KT, and this will be plus mu naught KT epsilon A. So let us simplify this further. We get SA into sigma A by E minus, plus mu KT sigma A by E, and then this will be, these two terms are left, so I'll just put them here. So this will give us minus mu sigma T by E minus KT sigma T by E. So this is what I get. Let us simplify this further. So delta R by R gives us SA into sigma A by E. If I were to take this common, SA sigma T sigma A by E. So this gives me 1 plus mu KT. And I take this as sorry, here it will be plus. Since we have not substituted, since we have not yet substituted for the Poisson's ratio, this will be plus. So this will also be plus. It follows that this quantity will be negative. So this is positive. So if I were to cross multiply this out, what I get is delta R by R is equal to SA sigma A by E into 1 minus mu KT. Basically, I have accounted for these two in this expression. And then I get plus SA sigma T by E into KT minus mu. So we get this expression directly. Now in order to nullify this, that is, it can be clearly seen that if I can nullify this from the change in the resistance, I can directly measure the stress. So therefore, if Kt is taken equal to mu, then delta R by R directly gives us Sa sigma A by E into 1 minus mu Kt. So this directly gives me a measure of the stress instead. So this acts as a stress gauge. And this is made possible when Kt is equal to mu. So therefore, in the question, the stress gauge construction is based on the transverse sensitivity of the gauge being equal to the Poisson's ratio of the gauge substrate. So when this happens, we can directly measure the stress instead. So let us take a look at this question. Match the type of strain gauge to the correct corresponding figure. Delta rosette, torque rosette, stress gauge, and rosette for hole drilling is what is given. Now on the right side, we can see actually delta rosette is which is at equal angles to our coordinate system. So we can clearly see here that we have a delta rosette here. So A goes to 3. Now what do we know about this rosette of hole drilling? That this is used to measure residual stress or strain. So we will initially paste this on the surface and then drill a hole in the middle, and whatever stresses get relieved, they will actually be captured by the strain in these three strain gauges. And since we have to populate the strain sensor, this happens to be the ideal choice for that. And we are actually talking about measuring the strain at this point where we will be drilling the hole. So this is the gauge for measuring the residual stress by hole drilling method. So we have map 2. Now if we see a torque gauge, essentially what a torque gauge is, when principal stress directions are known, what happens in the case of a cylinder? So let us say we have a cylinder like that, and this is subjected to a torque. So it closes like that, and this is subjected to some torsional moment, some torque. So essentially, if I were to see the state of stress here, I have a condition of pure shear stress state. So I have it like this. Now, if I were to transform this into another coordinate system, this can be treated as a combination of tension and compression of equal magnitude as that of the shear stress. So this will lead to a tension here and a compression here. We know that these are the principal stresses and they are orthogonal. So if we can measure the principal stresses or the principal strain, so to speak, along two orthogonal directions, we can actually populate the entire stress tensor in the case of this torsion. So we can see here that here the grid is aligned this way and the other grid is aligned like that. So this actually gives us a measure of the torque. So if we were to map it based on this, we will get A as the option. Granted that these choices may be subjective, but it doesn't hurt to know, at least just by looking at the strain gauges. If we are able to identify some of them, it will help us in the long run. Okay, so let us look at this question. In precise measurements, accounting for transverse sensitivity of a strain gauge is important. The strain gauge manufacturer has come up with a new configuration of the strain gauge to suit the application, and its transverse sensitivity factor Kt needs to be evaluated. So Kt, generally this is provided by the manufacturer. So they have come up with a new configuration of the strain gauge to suit some application, and Kt needs to be evaluated. The manufacturer has pasted two strain gauges on a tension specimen in the axial and transverse direction to make the determination. Okay. The ratio of the transverse to axial strain. So we have a transverse strain and its ratio with the axial strain is termed as C, capital C, which is found not to be equal to the Poisson's ratio of the material. So this is not equal to mu naught. Okay. Standard notation Kt refers to the transverse sensitivity factor. Sa is the axial strain sensitivity, Sg gauge factor, and so on. So we have been given all the expressions here. Now what is asked is what is change in the resistance that is expressed. Okay. So here let us take it that the change in the resistance is a function of the axial strain plus the transverse strain, and essentially we will be dealing with the shear also, but shear is decoupled here, so this goes to 0. So therefore change in the resistance is brought about by Sa epsilon A plus St epsilon T plus St epsilon T. So this follows that delta R by R is Sa. If I take Sa common, I get epsilon A plus St by Sa into epsilon T, which by definition is epsilon A plus Kt epsilon T. So delta R by R is Sa into 1 minus, or rather, let me take epsilon A also common, into 1 plus Kt into epsilon T by epsilon A. Now we know the general notion of epsilon T by epsilon A is minus mu naught. That is the Poisson's ratio. So delta R by R is Sa epsilon A into 1 minus mu naught Kt. So essentially what we do, we will push this to the end, and this entire thing we replace it by the gauge factor Sg into epsilon A. And this gauge factor is only to be determined, which is determined experimentally and supplied by the manufacturer centrally. So here the question says delta R by R can be expressed from which of the following. We can see that delta R by R is Sa into 1 minus mu naught Kt into epsilon A. So if I were to see these options, Sa into 1 minus mu naught Kt, I can get option D from here. Now let us see what the question further says. The change in the gauge factor Gauge factor is expressed as which of the following. So to simplify this expression, if I bundle this up into one neat expression, it gives me SA into 1 minus mu naught KT. SA into 1 minus mu naught KT is my SG here. So far, so good based on this. Now, the change in the resistance in terms of SG and C is which of the following is what is asked. So, this is the condition where when epsilon T by epsilon A is not equal to mu naught. So, what happens during that time? So, let us see what happens. So, one expression that we have already at our disposal is delta R by R is equal to SA epsilon A into 1 minus mu naught KT. So from here it follows that Sg is Sa into 1 minus mu naught KT. Or we can also write Sa is given by Sg divided by 1 minus mu naught KT. So far so good. Now in general when we make measurements using a strain gauge, it will essentially be having the transfer sensitivity effect embedded in it. So what we see is for this reason we define the actual the apparent strain as what is read from the strain gauge. From the strain gauge instrumentation. That is, we if we know delta R by R, we say it is Sg into epsilon A, but this epsilon A is the apparent strain that we are reading. This is not the actual axial strain that was of our initial interest. So that is why we term this as the apparent strain. So this is given by this expression. Now we also know from here, or rather from our strain gauge theory itself, that delta R by R is given as SA epsilon A plus ST epsilon T. So from here I can write this as SA into epsilon A plus KT epsilon T, which gives me delta R by R is equal to SA epsilon A into 1 minus 1 plus KT into epsilon T by epsilon A. And we won't replace this by mu because this is found to be not equal to mu yet for this case. So from here, if I were to solve this, solve for, or rather, if I were to simplify this, what do I get? I get this expression into this expression. So I get epsilon A is equal to delta R by R divided by this entire expression. So this I get as the actual strain. But in reality, we do not know the value of SA. From our strain gauge, we only know the SG. So let us replace what SA is in terms of SG. So we have this expression. we have this expression. Now, epsilon A, if we were to substitute, we have it as delta R by R whole divided by, I'll just substitute in place of SA, I'll substitute this. So I have here Sg into 1 minus mu naught Kt into 1 plus Kt into epsilon T by epsilon A. So this is the measure of the actual strain in a problem when there is a mismatch between epsilon T by epsilon A and mu naught. Now we can clearly see when epsilon T by epsilon A happens to be minus mu naught, these two will cancel out and our apparent strain will be equal to the actual strain. But due to this Poisson's ratio mismatch, or rather we should say that since the axial strain, since the transverse strain and the ratio of the transverse strain to the axial strain is not equal to the negative of the Poisson's ratio, this difference comes into the picture. So from here, if I were to see the change in risk, and in the question it is given in the question is epsilon T by epsilon A is some constant C. So I can just replace here in that constant, I can just put that C for simplification. So let us see what the answer comes out to be. It says change in the resistance in terms of Sg and C is given by which of the following is what is asked. Okay, so I have this expression, but actually the change in resistance is what is asked. So I'll just solve this one step further. I'll just cross multiply this. So I have this here, delta R by R is equal to, so I have this epsilon A, this comes here, Sg into epsilon A into this expression divided by this expression. So Sg epsilon A into 1 plus KTC divided by 1 minus mu naught KT, mu naught KT. So I have, so this is not correct, this is also not correct. These two have it correct, but this is epsilon T. So I have delta R by R is equal to Sg epsilon A. Delta R by R is Sg epsilon A 1 plus KTC divided by 1 minus mu naught KT. So we have this as the correct expression for this case. For this case. Okay. I hope that is clear. Should there be any questions, please feel free to ask. Okay. In the meantime, let us look at this question. It is proposed to measure mode 1 SIF in an aluminum alloy with Young's modulus E as 70 GPa with a Poisson's ratio of 0.333 using a single strain gauge. So essentially, when we go for a problem of a crack, for example, if we have a crack here, so we have a stress concentration here. So essentially, if we look at how the stresses vary, it has a very high gradient near the crack tip. So there will be a stress concentration here. So naturally, there will be, if there is a stress concentration, there would also be high strains. So here, the general way to predict the stress intensity factor, the stress intensity factor is something that characterizes the stress distribution or the stress field strength, strength of the stress field, I should say, characterizes the strength of the stress field in a problem with cracks. No problem with cracks. Okay. So generally it is a function of R and the crack axis is taken as the X, the positive X. So this is given to be theta, or rather I should, let me draw it this side. If this is X, some point at a distance, radial distance of R and an angle theta. So we have expressions for the stress and strain distribution around the crack, around the vicinity of a crack as a function of R and theta. And that field is characterized by something called a stress intensity factor. So generally we have three modes of opening. In the case of a planar problem, we will have two modes in which a crack can contribute to the stress field. One is basically by the opening mode and one is by the shearing mode. So one will shear against the other, and in the second case it will have a pure opening. So the superposition of these two will actually give the state of stress at any point. But in this problem, it is already qualified that it is a mode 1 SIF that we are trying to determine, which means basically there is opening. There is an opening mode that is at play here due to some far field stresses that are applied, but in the presence of a crack in this specimen. And we are looking at a point where we want to find the stress intensity factor using a single strain gauge. So this is the constraint here. In general, since there is a crack tip here, the stress gradients and the strain gradients are quite high. Ideally, we should not be measuring the stress intensity factor using a single strain gauge. We should have a series of strain gauges, and there are special strain gauges that come for this purpose also, where the gauges are where the grids are placed close to each other, and these are manufactured that way. But since we have only a single strain gauge at our disposal, we'll try to see how we go about doing that. Now at this point, that is at an angle of theta at a distance of r, if I were to take this as the axis, I place a strain gauge along this direction. So this is my strain gauge, let us say. The axis of the strain gauge is at an angle of alpha. So it says determine the orientation angle alpha and the position theta for making this measurement. Determine K1 of the stress gauge. Determine K1 if the strain gauge is located at a radial distance of R is equal to 2 mm, and the strain measured in this strain gauge, when we connect this to the strain gauge instrumentation, it reads a strain of epsilon equal to 750 mu. So this is given. Epsilon is 750, it is given. R is equal to 2 mm is given. So this alpha is generally selected in such a way that we have big expressions for the strains, epsilon xy. So at this point, we'll basically compute these three quantities. From here, using transformation, we will be calculating epsilon along this alpha, which is what a strain gauge would essentially measure. But we select alpha in such a way that that expression which we get towards the end, which has component of epsilon xx, epsilon yy, and epsilon xy, simplifies, and many aspects go to zero. So this derivation is given in detail in the lecture, so I will not delve into that. But essentially, once we try to extremize this and set it equal to 0, what we will get is cos 2 alpha is equal to minus of 1 minus mu divided by 1 plus mu, where mu is the Poisson's ratio of the material. So this is the expression we have in order such that many terms cancel out. So this is the orientation at which we will place the strain gauge at with respect to the x that is taken parallel to the crack axis here. So if we go about evaluating that, so I'll put this here. Selection of alpha such that the strain along direction simplifies. So with mu is equal to 0.333, we have cos 2 alpha is given by 1 minus divided by the same expression but with a plus. So this gives me minus 0.667 divided by 1.33. So cos 2 alpha is minus half, which gives me alpha is cos inverse so alpha is, or rather this is 2 alpha, so this comes out to be 60 degrees. So alpha is 60 degrees for this. So once we have the crack, once we have the crack, we will have this orientation at 60 degree. Further, now for this question, for this position, so the first coefficient of the multi-parameter equation for the strain field would disappear when tan theta by 2 is minus cot 2 alpha. Now one might wonder where these expressions are directly coming from. For that, I would suggest that the viewers see the lecture once for the derivation, because essentially this has its roots in fracture mechanics. So how this is evaluated, but for the sake of the application, professor has included that in the lectures also. You can just take a look. So this gives me tan theta by 2 is equal to minus cot 2 alpha. So I know that alpha is 120. So this gives me alpha is 60. So this gives me cot 120. So from here it follows that theta is given by 2 times tan inverse of minus cot 120 into 2. So for aluminium, this also comes out to be 60 degrees. Now, after having done this, we have a straightforward expression for mode 1 SIF we have a straightforward expression given by K1 is E into 8 by 3 pi r into the strain measured along the alpha direction. So let us go ahead and compute this. So in the question, it is given that this is the strain gauge is pasted at a radial distance of 2 mm, and we have already seen it is pasted at an orientation of 60 degrees, from which we have our alpha as 60 degrees. So it is pasted parallel to that. And then we have epsilon that was measured to be 750 microstrain. This is given. And we are doing this for aluminium, which has a E of 70 GPa. So therefore, K1 comes out to be 70 E3 into 8 by 3 pi into 2 mm. So I'm just using consistent units because in the question it is asked, SIF is asked in MPa root meter. So I'm just substituting in consistent units. This into 750 microstrain. So what does this come out to be? So from here, K1 comes out to be, we'll just calculate 8 by 3 into pi 2 into 10 power minus 3 root over into 70 into 10 power 3 into 750 into 10 power minus 6. So this comes out to be 6.795 or 6.8 MPa root meter. 6.8 MPa root meter. So once we have K1 at our disposal, we have expressions as functions of r and theta, which is just scaled by K1, and we will have the strength of this stress field that we will have. That we also remember from photoelasticity, we will see it in terms of isochromatics like this for K1 case, for the opening mode case. So this is just to illustrate and elucidate an example where using a single strain gauge, one can calculate the strength of the stress field around the crack tip. Let us look at another similar application, but this time we are not going for a much complex problem as we saw as a crack. So here we can also try to derive this from first principles. So this question says that the gauge factor of a strain gauge is 2. So SG is 2 is something given in the question. SG is 2 is something given in the question. The transverse sensitivity of the gauge is given as 1.1%. So KT, which is ST by SA, is given as 1.1%. Okay. The strain gauge is used to measure the hoop strain of a thin pressure vessel whose Poisson's ratio is 0.29. So mu of the specimen or the vessel is 0.29. This is given. The Poisson's ratio of the calibration beam material is 0.285. So this KT would have been based on some expression that the manufacturer did, and that was done on a beam whose Poisson's ratio was 0.285. So this is the case where we will actually have a mismatch in the Poisson's ratio. So we will see what is the implication of that. So this question asks, what is the ratio of the longitudinal strain to hoop strain in the pressure vessel? So let us see what it is. I'm sorry. Yeah, so I'll just add a new page. So I have Poisson's ratio like that. So in the case of a pressure vessel, yeah. So in the case of a pressure vessel, I have hoop stress is given as PR by T, where T is the internal pressure, R is the mean radius of the vessel, by assuming that it is a thin cylinder, not a thick cylinder. T is the thickness of the wall. So the assumption is that R by T is much, much greater than 1. Thickness is extremely small as compared to the radius. So that is when this expression holds. Similarly, we have the longitudinal strain as PR by 2T. Okay, so from this we follow from Hooke's law. In the question we have been asked what is the ratio of the longitudinal strain to the hoop strain in the pressure vessel. So let us calculate that. So the hoop strain given as hoop stress by E minus hoop mu of the vessel. I'll just write mu V, hoop longitudinal by E, where mu V is this. V is this. This is to be kept in mind. Okay. Similarly, we have epsilon L is equal to sigma L by E minus mu V sigma H by. So let us go ahead and substitute this epsilon H. So this gives me PR by T minus mu E PR by 2T. So if I were to take PR by T common, I get 1 minus mu V by 2, which is PR by T into 2 minus mu V by 2. So this is equation A. Similarly, if I were to calculate this, so epsilon L comes out as PR by 2T minus mu P PR by T, which follows PR by T into half minus mu V. So this comes out to be PR by T into 1 minus 2 mu V by 2. So this is equation B. So the question is asking for the ratio of the longitudinal strain to the hoop strain in the pressure vessel. So the longitudinal strain is this expression divided by the hoop strain is this expression. So this gives us 1 minus 2 mu P upon 2 minus mu V. So this is the ratio of the longitudinal strain by the hoop strain. Now, why is this important? As we saw, if there is a Poisson's ratio mismatch, then we need to evaluate this ratio, and this won't be exactly equal to the Poisson's ratio of the specimen material. So from here, it follows that this ratio epsilon L by epsilon H is given as 1 minus 2 into mu V is 0.29 by 2 into 0.29, sorry, 2 minus 0.29. So therefore, epsilon L by epsilon H is given by 1 minus 2 into 0.29 divided by 2 minus 0.29. It comes out to be 0.245. So we have this as 0.245. Very well. So we are clearly able to see this is not equal to the actual Poisson's ratio of the material. That is only applicable in the case of uniaxial tension. So what is the apparent gauge factor is what is asked. Now we know that apparent gauge factor can be determined by the apparent strain by, or rather apparent strain, I won't say it like this. What I instead do is the apparent gauge factor into the apparent strain gives me the change in the resistance. So the apparent gauge factor can be written as Sg divided by 1 minus mu naught Kt into 1 plus Kt into epsilon T by epsilon A. Now when epsilon T by epsilon A happens to be mu naught, or rather minus mu naught, this waters down to the same expression as the gauge factor. But since that is not the case here, so we will just see how to go about solving that. So we have the gauge factor as 2 into 1 plus Kt is given to be 1.1% in this question. So this is 1.1 by 100 into epsilon T by epsilon A comes out to be 0.245 divided by 1 minus mu naught for this material, for the foil, is given as 0.285 into 1.1 by 100. So Sg cap comes out to be, so 1.1 by 100 into 0.24245. So we have 2 into 1 plus 2.695 into 10 power minus 3 divided by 1 minus 0.285 into 1.1 by 100 gives me 3.135 e minus 3. So we have Sg is equal to 1 minus this into 2 to 1 plus 2.695 into 10 power minus 3. So this comes out to be 2.01, 2.012. So this is clearly not equal to the gauge factor because of this Poisson's ratio mismatch. So it is a little more than that. So what is the percentage error? So the question asks 1012. What is the percentage of error introduced if the transfer sensitivity effect is not taken into account? So the error introduced if the transfer sensitivity effect is not taken into account is, or rather let me say error like that, apparent strain minus the actual strain by the actual strain, which in terms of Sg, if I were to see, in terms of the values, if I were to see, I get this as Kt into epsilon T by epsilon A plus mu naught divided by 1 minus mu naught T. How we get this expression? We already got the expression for epsilon A when we had derived it earlier in one of the questions. I will just show where it is. The transverse apparent strain, we have it. Yeah. So we have the actual strain and the apparent strain. So from here, we can actually arrive at this expression for the error. So let us go ahead and calculate this. Error in percentage is given by Kt is 1.1% into epsilon T by epsilon A came out to be 0.245 for this question. So this is 0.245 plus mu naught for this question is actually 0.285. It is given over here is 0.285. So this is 0.285 divided by 1 minus 0.285 into 1.1 by 100. So the percentage error is evaluated as 0.245 plus 0.285 into 1.1 by 100 divided by 1 minus 0.285 into 1.1 by 100. So we are talking about percentage error. So naturally we will be having into 100. So this comes out to be 0.58 or 0.585%. So this is the error is less, but nonetheless it is not zero because there is a slight change difference between the Poisson's ratio of the Poisson's ratio used in calibration, Poisson's ratio is the actual problem. So I hope that is clear. Yes, sir. Hello, sir. Please go ahead. Okay. Yeah. Okay. So you have taken, yeah, that's fine. Anyway, we are talking about the error, or we can consider it to be the absolute error. So which one comes first, you're asking, is it? I see. Okay. So is there anything like absolute error mentioned over there? Okay. Yeah. 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 Okay, yes. In a sense, it will be the deviation with respect to this. So I should be, yeah, yeah. No, no. What you're saying is fine. So I'll just put the cap there. So perhaps, anyway, I suppose you get the spirit of it. So we are looking at how much difference it is trying to make when we try to ignore this effect and how the correction has to be done. So anyway, if there are any questions on this, sir, I welcome them. So I hope, other than that, perhaps I hope that I've done some justice to explaining what this course entails. If there is any feedback that you have on my delivery or what I should have covered, is there any shortcomings, I would welcome them. So that very well. Okay. Yeah. Yeah. I see. Okay. Okay. Very well. Right, sir. Thank you. Right. Right. Thank you very much, sir. So I hope, I'm happy to hear that. If that has served some purpose and you've taken some substance out of it, I'm happy. Uh, So other than that, yes, sir. So these questions I will definitely address on Thursday. So we'll take it from there. So other than that, if there are no further questions, perhaps you can consider calling it a day. Right, right. Good day, sir. I'll see you. Thank you.